Hey everyone, this is a video lesson that I'm using for my AP Calculus AB class, but I'm posting it online just in case it would be helpful to others as well. This is the last section of our limits unit, and I'm really excited about this lesson today. Not because it's the last section. I mean, it is nice to complete something and have that sense of accomplishment, but the real reason that I'm excited about this section is because it's going to further develop something that we discussed at the very beginning of the unit, and that is the idea of an instantaneous rate of change. And this is something that is foundational to understanding calculus. You're going to see this formula that I'm going to show you today, again at the beginning of the next unit, and you're going to see it throughout our discussion of what's called differential calculus. So it's really important that we understand it, and so we start that discussion very early. Let's jump in with something that maybe looks familiar. Notice that we're starting with what's called example 8. And that is because this is example 8 from section 2.1, that lesson. So we looked at here a rock that was breaking loose from the top of a tall cliff, and our question was, what is the average speed during the first 2 seconds of fall? So we're going to go over this problem again. We already did it in section 2.1, but again, we're going to see it here just as a starting point to then move into instantaneous speed, and then move into something new, and that is a formula that you'll see. All right, but again, let's start with something we know how to do. So I'm going to grab a pen. Okay, and I'm looking at the average speed during the first 2 seconds of fall. So what I always like to do is I like to start with what is my time interval. If it's over the first 2 seconds of fall, that means I'm starting with a time of 0, and I'm moving toward a time of 2. So I'm setting up my interval from 0 to 2. Oh, I'm not good at writing today. I'm never good at writing, I know, but some days are better than others. Okay, and what we do from here is we set up 2 ordered pairs. So we're going to use this formula. Y equals 16t squared is our function that shows the height versus time. And so if we have a time of 0, 16 times 0 squared gives us a height of 0. If we have a time of 2, we can find that the rock fell, what? 16 times 2 squared. 2 squared is 4. 16 times 4 is 64. And then do you remember what to do from here? If you are asked to find an average rate of change, that's finding the slope between these 2 points. And so we can just set up our slope as y2 minus y1 over x2 minus x1, and that will find our average rate, or average speed. So that gives us 64 over 2, or 32, and the units would be feet per second, I think. Yes. Okay, so that's just a quick little review of how to find average speed. And then what we did from there was we moved on to find an instantaneous speed. So right here, I'm just going to remind you of how we started to look at this example in section 2.1. If we're asked to find the speed of the rock at the instant t equals 2, just a reminder because it's important, the function is y equals 16t squared. Okay, we tried to approach it the same way we approached example 8, the last problem. We said, let's set up an interval of time, but if we're looking at the instant t equals 2, that means we're going over the interval from t equals 2 to t equals 2. And then we set up 2 ordered pairs. We said when time is 2, let's just go back and look at that. The y was 64. And we're going to the same moment in time. So again, 2 comma 64. Then to find our rate, we tried to do an average rate with a slope, 64 minus 64 over 2 minus 2. And I'm doing all of this knowing that it's not going to work because I want to remind you of something really important that happens. What we get out of this is 0 over 0. That's a 0. And that's really important because remember, that's an indeterminate form. And indeterminate form means that we should be able to find an answer to this problem. Is there a speed to the rock at exactly t equals 2 seconds? Yes, there is. We should be able to calculate that, and that's like one of the essential questions here in differential calculus. How do we do that? Clearly, we can't go from 2 to 64 to 2 to 64 because we get this. We get 0 over 0. But here's something that we could do, and I hope this looks familiar if you were with me for section 2.1. What we could do is we could say, well, we can't use the interval exactly from 2 to 2, so let's use something like 1.99 to 2, or 1.999 to 2 would be even better. Or something, with 2 at the beginning at the left endpoint and a little bit of a later time, like 2.01, 2.001 would be even better. And that'll give us an approximate rate of the instantaneous speed at t equal 2. And it's pretty good. So what I'm focusing on, well, first of all, I should mention this. My calculation here is still just doing slope between two ordered pairs. Okay, it's really important to keep that in mind as we go through this lesson, that we are trying to do slope at one point. Okay, so we're still trying to do y2 minus y1 over x2 minus x1. We're just trying to do it with 1 point instead of 2. And, one of the big questions is, how do we do that? This is one way that you can do it. You can approximate it. And if you take a look at your rates now, you can kind of see that 2 to 2, the interval from 2 to itself would fall in here. And it looks like what that is coming toward from each side is 64 feet per second. Okay, so that's one way that we can get the answer. Now, again, if you were with me for section 2.1, you may remember that that was a pretty long and grueling process where we had to do all of these calculations just to be sure that this is the speed of the rock at time 2. What I want to show you today, and this is the new stuff, is that there is a formula that will get you the exact instantaneous speed of the rock at time 2. And the reason we have it in this unit on limits is because the formula uses a limit to get there. Okay, this is a numerical approximation of a limit. What you're going to see today is an actual formula of a limit that uses a limit. Okay, so what I want to do here now is I want to kind of set up where this formula comes from, and then I'll show you the formula. So keep in mind that, this is what we're trying to get at. We're trying to get an interval from 1 point to itself, find that speed from 2 to 2, and we tried to just set up two ordered pairs, and that didn't work. So what we do instead is we say, let's adjust our interval just slightly. Let's start at time t equals 2, and let's go to time 2 plus h. Okay, now h can be any amount that you add on to one of the endpoints, and I always choose to add it on to the right endpoint. Okay, now if you think about it, like going back to this, you want h to be small, right? You want to have an interval that is pretty close to being a 2 to 2 interval. So h could be something like 0.01. Take a look at this one. That could be our h here. H could be 0.001. You could add the h to the left endpoint. That would be approaching from the left-hand side. And so you could say, let's have an h value of negative 0.01 or negative 0.001. And so that's what this h means. Now, understanding where this h is coming from is pretty important. So if you have questions about that, please let me know. Because it's key, like this is clutch right here, all right, knowing that you're going to put a plus h in there, and that is going to take you into the formula that you need to use here. Okay, so now that we have a new slightly different interval set up, we can just keep going like we were doing with this example. Going back, this one, we're going to do this like we were doing with this example. We're going to do that, okay? We are going to, from an interval, we are going to set up ordered pairs. We already know, because we did it numerous times, that this is the ordered pair 2, 64. Oh, I should probably note yet again that the function is y equals 16t squared here. We just keep using the same function at first because it's easy to see the development of something if you just stick with one function. Then we'll branch out to other functions, okay? And then, what's going on here? Well, the x-coordinate or the t-coordinate is 2 plus h. How do we get the y-coordinate? Well, you get a y-coordinate by taking your x-coordinate and inputting it into the function, right? Or the t-coordinate in this case. So I'm going to take 2 plus h and put it into my 16t squared, and it looks like this. 16 times the quantity, 2 plus h squared. There's my y-coordinate. Okay, this just gets so exciting for me. I'm like, yes, you're almost there. You're going to get the formula. You're going to see it. Okay, and now what we're going to do is we have an x1, y1, x2, y2. Like, just to be very clear here, because I don't want you to lose sight of this fact, I am doing slope x2, y2. I'm doing slope. I'm doing m equals y2 minus y1 over x2 minus x1, something that you've known since pre-algebra or even earlier. Okay, that's what we're doing. So in this case, our slope would be 16 times the quantity 2 plus h squared minus 64. That's my y2 minus y1 over x2 is 2 plus h minus x1 is 2. Okay. So that's the beginning of understanding the formula. You need to understand that you set up an interval from a point to a point that has a slightly later point in time, and the way you get that is with the plus h. From there, you go into your ordered pairs and you set up the slope. Now, you may be thinking to yourself, okay, well, how am I going to get a number out of that? And actually, keep in mind, we know what number we should get out of that. Look. We should get 64 as our answer. Okay, somehow we're going to take this formula and get 64. I remember in some years I have students say, well, it's just right there. Look, it's right there. It's actually not always just going to be right there. All right, sometimes I think this is kind of a bad example. I should come up with a different number because, yeah, I know 64 is right there. That's not it, though, okay? What we're going to do now is we're just going to do some simplifying and then talk about where to go from here. Let's do something really basic to simplify. I'm going to take this up here. Okay, look at the denominator. What happens in the denominator? You see a 2, you see a minus 2. Are you okay with this? Those would cancel, right? 2 minus 2 is 0. So all we have in our denominator is an h. Okay, pen, don't die on me now. All we have in the denominator is an h. And that's always going to happen, by the way. Okay, that's always going to happen, that you're just going to end up with an h in the denominator. So when I finally show you this formula that we're going to be using, I mean, we're developing the formula, but I'm going to show you on the next slide what the formula actually looks like. You're going to see in the denominator just an h, because that x2 minus x1 always simplifies to h. Okay. In our numerator, I'm going to do a couple of things. The first thing I'm going to do is, let me grab a different color. I am going to expand this. I see a quantity, a binomial quantity squared. I'm going to expand that. So I'm going to bring my 16 in here. And hey, keep in mind, 2 plus h squared is not 4 plus h squared. You can't distribute a power through a binomial. It's like what, I don't know, 25% of all math memes are made out of, right? That mistake. Okay, you have to do this. You have to do 2 plus h times itself. You have to distribute that, or FOIL, whatever you want to call it. And what you're going to get out of that is 4 plus 2h plus 2h plus h squared. Right, this is like algebra 1 stuff. And then we can combine these like terms and get 4h here. So that's what I'm going to write in the parentheses. I'm going to write 4 plus 4h plus h squared. Bring along the minus 64. Okay. Finally, something else that, I guess not finally, but we're getting pretty close to getting our answer here. I'm going to distribute the 16 through the trinomial that I have in the parentheses. 16 times 4 is 64, right? Yeah. 16 times 4h is 64h. 16 times h squared is 16h squared. Bring along the minus 64, and you still have all over h. Okay, I hope you notice at this point that this cancels, 64 minus 64. And if those two constant terms cancel, then what you can do with this part that remains is you can factor in h, a common factor of h. Now, the greatest common factor is not h, but I actually suggest that you just factor out an h so that you can kind of see what's going to happen here. Okay, so what we're going to have is h times 64 plus 16h all over h. Okay, so once again, recap, I canceled the 64 and the minus 64. I noticed that these two pieces are what's left in my numerator, and so I decided to take an h out of them. The reason I take that h out is because then I can do this, right? Yay. And so now I've simplified this slope formula. Okay, remember, this was all just coming from setting up two ordered pairs and finding the slope. I've simplified the slope formula to 64 plus 16h. Now, remember, we know what the answer is. It's 64, right? Okay, do you see it there? It's right here. The question is, what do we do with this piece? Well, this is where a limit comes in. Oh, yes, remember we have those things called limits, and they're pretty important here. Okay, it's really important, actually, to the concept of finding instantaneous speed. Going back to our approximation method, okay, remember that I said that the h is whatever you're adding on. So the h is like 0.1, or if you want to get even a better approximation, you could say let's add on 0.001, or if you want to get an even better approximation, you could say let's add on 0.0001 or so on. And what I want you to notice there is that to get a really good approximation, your h is getting smaller and smaller. 0.01, 0.001. You know, here we're at negative 0.01, negative 0.001. Okay, we're trying to come into an h value of what? What do we want the h to be? If we're trying to model here an interval from 2 to itself, what do we want the h to be? We want the h to go to 0. I really hope that you're like saying this. This is the one moment where I hate teaching on a video like this, because normally if I'm in class, I can see you all saying, okay, it's going to be 0. You know, I don't know if you're saying that or not, but you should be. Here's the limit that we want. We want the limit as h goes to 0. And that's going to get us our final answer. Now just hold off on that for a moment. I know that's unsatisfying. We're not finishing this. But bam, look at that. I needed to show you this. I'm just like, you guys need to see this before we finish. Look at that. Okay, this is the formula. Ew, I just said like bam, like, what's that guy's name? Never mind. All right. Here's the formula. This is what I am telling you is foundational to understanding differential calculus. Okay, you are going to see this formula a lot at the beginning of the next unit. We're going to call this a derivative at the beginning of the next unit. So derivatives are pretty important to calculus. And so what I want to show you, oh my gosh, though, I never noticed this. There is a huge typo here. It's, oh my, I'm so mad at myself for not seeing it until this moment when I'm recording. Okay, do you see the problem here? I just told you that the limit should be as h goes to 0. It's a 0. It shouldn't be x. What? Where did this even come from? I'm sorry. That should be an h right there. All right. Okay, so anyway, we have, I can't even continue now. We have a, here's our x coordinate with the plus h. Here's our x coordinate. It's, it just says a instead of the value 2 that we were using, but it's the same idea. Throw them into the function, and that gets you your y coordinates. So I just want you to remember, this is y2 minus y1. In your denominator, you did x2 minus x1, but we noticed pretty quickly that that simplified to just an h. So the h in your denominator is your x2 minus x1. And then how do we take it from 2 separate points to just 1 point? We throw in this limit, and the limit is as h goes to 0. That is how you find the instantaneous speed. That is how you find what is called the slope of a curve at 1 point. Okay. All right. So now I'm just going to sort of recap, and then I'll finish off the problem. So keep in mind, here's what we're doing. We're setting up an interval from time 2 to time 2 plus h, and we got our ordered pairs. And we just did y2 minus y1 over x2 minus x1. Okay, so that should all be familiar stuff. Setting up ordered pairs, doing slope between 2 points. That's all algebra. The calculus comes in, I can put the calculus in right here. The calculus comes in with this limit. And it says h goes to 0, not x. Okay. And from there, okay, that's how you're always going to set up these instantaneous speed or slope at 1 point problems for now. From here, you're getting an answer to a limit by just doing algebraic manipulation on the limit, which is something that you've practiced in this unit a lot already, right? So you're just trying to say, okay, let's try somehow to get an answer to this. Maybe we should note that if we fill in 0 for our h's, what we will get is 0 over 0. So you can't just substitute 0 in at this point. You have to do what we did, which was, let's expand the 2 plus h squared. Simplify the 2 minus 2 down to h. So I have a limit here. It's good form to carry that limit along throughout. Distribute cancel factor and h. Again, we're not really concerned with greatest common factor. Doesn't matter if you do greatest common factor, you'll be okay. You'll still get the right answer, but really we just want to factor that h out so that it cancels with the h in the denominator. Remember, we're trying to make h go to 0, so I'm pointing like you can see. You don't want this h to be here. Right here, you don't want this h to be here because we're trying to sub 0 in for h. So we need to get that out of there. That's like a secondary goal of yours. After you do all this, you're basically trying to get that h out of the denominator, and that will give you an opportunity to then substitute 0 in for h. So when I get down to this very simplified form, I can say my answer is 64 plus 16 times 0. Again, that's a 0. My zeros always end up looking like 6s. And that gives me an answer of 64 feet per second. Yay, we did it. Okay. I hope you can see that. Is my picture right here? Can you see me? Can you see that? All right. Anyway, maybe I should do this. F10. Here we go. All right. There's your answer. All right, so I want to show you before we completely move away from this problem of specifically using the formula y equals 16t squared at t equals 2. I want to show you one more thing, and that is what we are doing here graphically. Okay, so if you've ever taken a physics class, you may have heard that, you get the speed. If you're looking at I should say, a distance versus time graph, you can get the speed at, over an interval or at a point by finding the slope, right? So there's two in particular types of slopes that we find here in AP Calculus. So I'm going to grab a line. Let's see if I can do this. Okay, we don't want the line to be very thick. And what color do we want the line? Let's make the first line red. Okay, when I asked you at the very beginning of this section to do a average speed over the first 2 seconds of fall, what you're doing is from t equals 0 to t equals 2. This is 0, 0, this is 2, 64. And that line, when you have a line that goes through 2 points on a curve, that is called a secant line. This is called a secant line. And for the average speed, you're just doing the slope of the secant line, which again is going through 2 points, so you don't really need the calculus there, the limit there. Okay, however, if I ask you, going back to my line, gotta set it all up again. We'll do blue this time. Oh, it's done. All right, if I ask you for the speed at t equals 2. All right, that didn't work, but I can move it. That's finding the slope of that line. Okay, I wonder if I can make it bigger. Awesome. I'm not ready for that. Sorry. Yeah, I can make it bigger. Okay. All right, that'll have to do. And there's a couple things in particular that I want you to know about that line. First of all, that line has a slope, right? So you should be able to calculate the slope of that line. Second of all, I want you to notice that that slope is steeper, right? And so I hope that makes sense in what we did. We, found the slope of, first of all, the interval from 0 to 2, which again was the secant line, and we found that to be 32. And then we did all of this crazy work, and we found the slope of this line to be 64, which would make sense because it is steeper. Okay. The third thing I want you to notice about this, it came up with one other thing that you should notice, is that this line is just going through 1 point on our curve. And a line that just goes through 1 point on the curve is called a tangent line. Okay, so as you continue to study calculus, you are going to see a lot of questions in a lot of different forms, and a lot of those questions will be asking you to find this. Okay, a couple of ways that we've seen it so far, or that we've discussed today, is instantaneous speed, or any instantaneous rate of change. You could call it slope of a curve, you could call it slope at 1 point, or you could call it slope of a tangent line. And like I said, in the next unit, you're going to start to hear this being called a derivative. Okay, it's all the same thing. So finally, let's wrap up with one more little example. And just so you know, in this example, I do a quadratic function again. I'm doing a really basic one just to show you the really, like, the basics of the formula that we're using here. Okay, and then what you're going to see in a practice that I have with this video, okay, I have a link to this in the description of this video. The practice that you're going to see will start to explore other functions. And what you need to know is, if you start to look at other functions, basically you're doing the same setup, and then you're just figuring out how to manipulate what is inside the limit to find your answer. Okay, I don't want to spend too much time in this video talking about that. What I'd rather do is just recap with one more simple example, and then we'll use the practice to look at some other types of functions. Okay, so two parts to this question where we're just looking at the function y equals x squared, or f of x equals x squared. The first part is, what is the average rate of change of the function over the interval 1 to 3? You're going to see a lot of those questions in the practice because I want you to remember the average rate means you're doing a slope between 2 points, or in other words, the slope of a secant line. And so what we would do here is we would set up 2 points. The left end point is 1. Throw that in here. 1 squared is 1, so that's my y-coordinate. The right end point is 3. Throw that in here. 3 squared is 9, so that's my y-coordinate. So we just did, we split up our interval into 2 ordered pairs. And then again, if you see the wording average rate of change, that means just find the slope between those 2 points. So y2 minus y1 over x2 minus x1, 9 minus 1 is 8, 3 minus 1 is 2, and so the average rate of change is 4. Just to be real quick here with time, I'm going to grab the graph of y equals x squared. Okay, and we'll paste it in here. Just to remind you that what we just did was we found the slope of this line. We started at 1, 1. We went to 3, 9. And we found the slope of this secant line. Two points. Oops, didn't want that. Sorry. Okay. Next part, what is the slope of the function at just the point x equals 3? So I'm going to draw that line in ahead of time. Let's use purple. Why not? Purple. At just x equals 3, what I want you to see, I'm going to have to do this and then move it because I'm not good at this. Yeah. Okay, this isn't the best, but it's supposed to show you that it's a little bit steeper. It's slightly steeper. I didn't draw it really great. I can move it around maybe to, there we go. Should have a computer do this for us. Okay, so you should be getting a slope that is slightly higher, and the way that we're going to do that is our new formula. Now, one of the common mistakes that I see with my students, I didn't do purple, is that they try to just go straight to that formula that I showed you and figure out how to fit everything into this formula. They see a formula, they're like, okay, if you're telling me there's a formula, I could just put the things into the formula and get my answer out, right? I suggest you don't do that because that sort of loses the idea of what you're doing here, and you might get frustrated and forget what you're doing. And it's not something brand new. You're not doing anything really that brand new here. What you should do instead is what we did for the the rock problem. We're saying let's start at x equals 3 and go to, we can't go exactly to x equals 3, so let's go to 3 plus h. Let's, from there, set up our ordered pairs and do our slope. Okay, the ordered pairs would be 3, 9 again, and 3 plus h, comma, 3 plus h quantity squared. Take the x coordinate here, put it into the function. The function just says square the x, and so that's your y coordinate. This is x1, y1, x2, y2. Set up a slope between those 2 points. 3 plus h squared minus 9 over 3 plus h minus 3. Finally, remember that you have this h in here and you don't actually want that h to be in there. You would rather this be the interval from 3 to itself. So how you take care of that is you throw in this limit as h goes to 0. And that will give you your slope at x equals 3. At this point, you're just doing some algebraic manipulation. The denominator always becomes h. And we are going to, again, expand 3 plus h squared, or, FOIL that. Expanding a binomial, you have to FOIL. So that's going to be 9 plus 3h plus 3h. So that'll combine to 6h plus 6h plus h squared. Bring along the minus 9. Oh, and I forgot to write one more time. I have a limit here. Can you see what's going to happen? Maybe you can even find the answer. The answer is, one of these numbers in here. Which one is it? Well, these are going to go away. What's left has a common factor of h. Whoops. I messed up. We're taking that h out. There's one more there. Right? 6h plus h squared. That could be written as h times quantity 6 plus h. Then the good stuff happens. Those h's cancel, and you can sub h into what remains. And so your answer here is 6. Yay. And so that purple line that I was trying to draw on the graph there has a slope of 6. Okay? As usual, I hope this was helpful, and let me know if you have questions. Bye.